in a circuit, how it flows through metal and through its conductors. Today is resistance, and that's the opposite of current. So who talked about, remember we talked about types of energy that could be given by a generator or by a battery we looked at? Remember the generator, what was an example we used for the generator? The simplest one that we said.
Provide electricity for a house?
Yeah, for a house, right? You have to turn some sort of a crank that induced some electric current through the using the magnetic poles. Now, think about like a dam and a river. What does a dam do?
Stops the water.
Yeah, that's what a resistor is. That's exactly what it is. So when we're in this unit, when we're thinking about resistance, think about the water flowing through a river, and when it hits the dam, it slows it down, right? And the water starts doing this, and then it goes through, and then it comes out the other end. That's what a resistor is. It slows down the flow of the electricity through the circuit. The electricity slows down in there, the electrons are slowing down. Again, we know they're going at a very slow speed as it is, and it uses that. It uses that energy. Now, a lot of resistors are things that we like. We have to have them. So a light bulb acts as a resistor in a circuit. In your circuit board in your computer, you have resistors in there specifically to slow down the flow of the electrons, to slow down the current in the actual circuit. What happens, Julian, you made this comment yesterday, if you don't have a resistor, if it's not working well, what could happen? You get a what?
Short circuit.
Short circuit. When there's a short circuit, the current is flowing too fast, there's too much current, okay, and it overloads the circuit, and that's where you could have like an electrical fire start.
So, I have a question. If they give you, if a question says like, doing I equals changing Q over T, for Q, if they just say like 3, like a number of electrons, you have to divide it by, because Q the charge.
Yeah, so if you have like 20 electrons, you need to multiply that by the charge on each electron. Negative 1.6 times 10 to the negative 19, remember the fundamental charge? You need to multiply that by 20, because there's 20 electrons, then divide that total charge by the time period that you're looking at. Okay? Alright, let's look at resistance now in the case of 19.2. So again, if the notes aren't up, I understand that, guys. It's tough for you to get them without the internet. But have blank slides for now. So we're going to calculate resistance, current, and what's called potential difference using our definition of resistance. We're going to distinguish between ohmic and non-ohmic materials. Okay, ohmic comes from what's called Ohm's law. We're going to see that today. We're going to look at the factors that affect resistance and discuss superconductors and their resistances. And we talked about them, if you remember, when we talked about conductors. We alluded to them. But let's talk about them further today. So first, the definition of resistance is what we just said. Is the opposition of flow. Opposition, okay, of flow in a conductor. Voltage. Now, where have you heard the term voltage?
Light bulb.
Yeah. When you buy a light bulb, what do you usually look at? The wattage is the power, believe it or not. But you do look at the watts when you buy it, that's true. But there's another parameter that you also look at.
Okay, sorry. Those are the follow-up questions for us. If it's negative 1.6, will that time be negative? If they give you I, they do that.
The current is just going to be negative in the end. That's fine. It just means it's flowing in a certain direction. Time can never be negative. So the answer you'll get will be negative in the end. It'll be a negative over a positive. I'm on this, though. I'm not taking those questions. You had last period tonight. Okay, it will be negative, though. So where have you heard voltage, James?
Voltage in lots of things concerning electricity.
What's the easiest example? What do you put in your calculator?
Battery.
Batteries. They offer voltage, don't they?
I just go AAA, AA.
Oh, all right. Well, there's a voltage reading on them. So have you ever gotten a 9-volt battery?
Yeah.
You call that a 9-volt battery because you know the voltage, but that's the actual amount of potential difference between the positive and the negative anode. So you have the positive and the negative ends of the actual battery, right? Those two prongs on the 9-volt battery. Potential difference is really just the difference between their charges from one to the other.
So volts and electron volts are the same thing, right?
Electron volts are a different unit. It's a different unit. That's all it is.
But this is why lightning works.
This is the way lightning works?
This is why it works.
Because there's a potential difference between
the ground
and the cloud. And now, lightning is a little different though, so I'm not going to get started in a conversation, but that uses ions. They're ions, they're charged. And we talked about that yesterday, so if you want to wait, because I know you weren't here. So wait till you read, but I talked about electrolytes and ions in the video. So that's the part with lightning. But to define voltage, we say it's when a positive charge flows through a circuit, each coulomb of charge gains some amount of potential energy in joules. Okay, and this is the ratio of energy gain per coulomb. So really what we're looking at is the difference between one end of the circuit and the other end of the circuit. Okay, that's what the actual voltage is in a circuit. Let's go on to Ohm's law to relate what these actually are so you can see what they mean. So Ohm's law tells us that the amount of voltage in a circuit or across a certain circuit element is equal to the current going through that element times its resistance. So let's say we have a light bulb, and the light bulb has a certain amount of voltage that it can take across it. It's a result of the current that's going through the light bulb times the internal resistance of that light bulb itself. Okay, the internal resistance of that light bulb itself. So the product of these two numbers. Now, Ohm's law tells us that, and if you think about it, as the resistance goes up, the voltage goes up. Right? As the resistance goes up, the voltage has to go up. They're directly related to each other. Now, traditionally though, you may have to use Q to get the current and then plug that in. Okay? Traditionally though, the resistance is something that is traditionally fixed. So let's start by redefining this by solving for R. If you solve for R, what do you get? Yeah, V over I. This is the way that we really want to be thinking about it. Although this is Ohm's law up here at the top, and that's the way you're going to see it. That's the way it's always been written as V equals IR. But this is what you want to think about. The resistance, again, is a property that is usually fixed in an element. So like a light bulb has a certain internal resistance. It's not really going to want to change. So what it does is this. If there's too much current, something has to happen to the voltage. If there's too much voltage, something has to happen to the current. So the bulb itself is usually a fixed value of R. So traditionally we want to say it's R equals V over I. It's thought of as the ratio of voltage to current. Okay, that's what the resistance really is thought of as. The ratio of voltage to current.
What does I stand for? Current?
Current. In the video last night I mentioned, because I didn't talk about it in class, current really was a long time ago called current intensity. That's where the I comes from. Remember I gave that bonus question with the P for momentum? I didn't give that question this time because you could find it in 2 seconds. But the current, the letter I, really comes from the word intensity. Because a long time ago in French, it had to do with the French translation. And it was the intensity of current. That's how they used to say it in French. And then the English system used current intensity. And in Britain for a long time, capital C was listed as current. But it eventually was adopted to be I because capital C is later thought of as what's called capacitance. Okay? So current is the letter I because it was current intensity. Okay? So you know what it is. Let's take a look at what Ohm's law tells us. Okay? What Ohm's law actually tells us. So, first, it's not a law that we actually find in nature, and it's really only valid for certain materials. We'd say that certain materials are ohmic if they follow Ohm's law, and they're non-ohmic if they don't follow Ohm's law. And what we can see here is from these graphs that we can see that the R value, remember if we solved for R, we said earlier that R was voltage over current, right? So in this graph, we're graphing the current and the voltage along the axis. Remember, potential difference, this is really voltage, V. And this is your I value for your current. If it does follow Ohm's law, what you get is a linear function. Right? Because this over this is always going to give you some R value. This is like your slope. Change in Y over change in X, except this happens to be change in X over change in Y. So if it is ohmic, the ratio of voltage and current for a given material has to be constant. And let me explain what I mean. Alright, so I've got a light bulb in front of me. And you're going to see this in the lab. We're going to do this when we get to circuitry. We're not doing this lab just yet because we haven't learned about circuits. But imagine this light bulb, okay? And I have a voltmeter or a variable voltage source, a variable battery. And I could sit there and change the voltage provided. So the light bulb is really dim because I have it on low voltage. And then I increase the voltage and I see the light bulb get brighter. And I increase the voltage more and I see the light bulb get even more bright. What's happening here is this. as I change the voltage, the current has to change proportionally. So if I double the voltage, the current here needs to get doubled in order to keep a constant R value here. Please look up. Please look up. A lot of you are just like, I don't know, unfocused. There's nothing. You don't have slides in front of you, so you should be looking up here. If I increase the voltage in the circuit and I turn up the power of the battery, the light bulb should get brighter. Okay, because the current is also increasing. If I double the voltage, the current should double because the light bulb has a constant resistance. The resistance in the light bulb is a property of its material. It's not changing. Now, if something was non-ohmic, like a light bulb that can have a variable resistance, it shows up like this on a graph. Because as I increase the voltage, I don't necessarily increase the resistance with the same proportion. Okay? I don't necessarily increase it in a way that causes my resistance to become constant. So, if a material, and a good example of a material like this is called a potentiometer, and what a potentiometer is, it's a variable resistor. And it's a resistor that works by using a sliding metal contact. If there's more contact of the metal if there's more contact of the metal that is overlapping each other, there's more current that could flow through it. If there's less contact, there's less current that flows through it. So a potentiometer could be a variable resistor, and that is non-ohmic. But something that is ohmic has a set resistance due to its material properties. And that's an example of like a light bulb.
So on an ohmic light bulb, there's like or something.
It's on or off.
So it wouldn't have any. It wouldn't be able to short circuit. But
No, it could short circuit. Anything could short circuit by two wires just touching each other. If two wires in the circuit touch each other and provide a smaller path or a shorter path of resistance, the circuit will short and it won't make it to the light bulb. So anything could short circuit. Yeah.
So, but does resistance change, like over time if temperature of materials change?
Yeah, and that's what we're going to talk about in a little bit, that although a light bulb has a fixed resistance, there are certain parameters that affect that resistance, like temperature of the ambient environment.
So every material that has a fixed resistance will have actually arranged by...
Nothing really has a fixed resistance. Exactly, James, you're right. So the idea is that it's fixed in its nature of its properties, but based on temperature, based on the length of the wire, based on the cross-sectional area, resistance then changes. Yep. Okay? So, but the idea I want you to know is this. As the voltage increases, the current has to increase with the same proportion. So if I triple the voltage, I triple the current. If I multiply the voltage by 5, the current has to go up by 5 for ohmic materials. For non-ohmic materials, that is not true. We're not going to go into what happens there, okay, because there are many possibilities, but the idea that it is not the same. And that's what this graph is trying to show you. The slope here, which they're showing as I over V, because the way they drew it, is the same as what I'm trying to show you, V over I. The slope is constant, and that slope is the resistance. In this graph, it's 1 over the resistance because these are inverted. Okay? But the idea, again, is that as the voltage doubles, the current has to double for an ohmic material. All right, let's see. I gave an example here at the very end of an example of something that is not an ohmic material, that has a fluctuating R value, and it's called a diode. And a diode just changes the direction of the actual current itself in the circuit. So a diode is like the example. Did we do it here? No, we did it in the other class yesterday. It's the example where the poles switch. Okay? One is positive, one is negative, and they can actually alternate. And that's where you get an AC current. That's where an alternating current comes from. Let's take a look at the next slide. Let's look at what James was just mentioning a moment ago. Factors that affect the resistance. Okay? Now, if we're looking at wiring in general, so imagine you have a piece of copper wire. Okay? There are 4 factors that we're going to look at. First, the length of the wire. The length of the wire. What do you suppose is the reason for the explanation up here that a longer wire has more resistance? What do you think?
Is it kind of like that same thing with the momentum about if you catch a ball with more time in contact, then it'll slow down and have a less hurt less force in hand kind of thing?
It's analogous to that. The ideas are right, yeah. The ideas are there, but explain it in terms of electricity now.
It means that, I don't know, the electrons will be flowing slower maybe, because it's a longer distance, or...
Well, remember, when we're looking at current here, or we're looking at, in this case, resistance, You want to think about material that's going to stop the flow. Does that help you at all?
So like more particles of length.
Yeah, a longer wire, there's more particles there to stop the flow of current. Right? There's going to be more collisions in that wire of the current. The current is going to move at a slower rate. So a longer wire has more resistance. Now, when it comes to circuitry, we're going to assume wiring in the circuit has almost no resistance. But this is important because a light bulb that has more loops has more resistance. Think about a light bulb, the filament. Isn't the filament just a bunch of loops? Have you ever looked at a light bulb before?
Yeah.
Do this if you haven't, please. Go home and look at an old light bulb, not the new incandescent light bulbs. The nice ones that are now the curly ones, you know?
Yes.
Those have gases in them. It's a little bit different. Look at an old school light bulb with a filament. You'll see the little loops. If there's more loops, the wire is clearly longer, right? So that would have a higher resistance. Okay, so the longer the wire. Now again though, when it comes to circuitry, we're going to see wiring. The wiring is going to be assumed to have no resistance because it's negligible compared to that of a light bulb. Okay?
No, go ahead.
Second, cross-sectional area. Anybody want to explain this one? Yeah.
Does this have to do with the area, like the surface area that the current has available to flow through?
Yeah, think about what we said for current. So the current, we said, if there was more area, it's easier for the current to flow, right? Think about a pipe. I've got this huge pipe and water's flowing through it. And suddenly it reaches a neck in the pipe where it narrows. What's going to happen? It's going to feel resistance, isn't it? It's going to slow it down. All that water can't go through there at the same rate. It's got to slow down here. It slows down going up to it, and then it shoots out much faster. But that's resistance. It's feeling slowing it down. So a smaller cross-sectional area indicates that there's going to be greater resistance. So we could say so far that length is directly related to resistance. Longer length, more resistance. But area is... Let's try that again. I'm prompting you. Listen, please. Length is directly related to resistance. More length, more resistance. But area is inversely related. Good, Luke. Inversely. Because as there's less area, there's more resistance. More area, exactly. There's more collisions. That's exactly right. Okay? There's not enough for it to go through. It can't go through that length. It can't go through that cross-sectional area as easily. Okay? Now, material also affects it. The material properties. So, who's ever bought an HDMI cable for your TV at home? Okay. When you buy them at the store, don't they range in price? They range from like $3 to like $20. What's the deal?
Because there's different materials.
What are they usually plated with?
Copper.
Gold.
Yeah, they're gold plated actually. A lot of them are gold plated. And yeah, the HDMI cables. Yeah, they're gold plated on them. Why are they gold plated? Gold has very little resistance.
Is gold one of the best materials for electric?
Say again?
Isn't gold one of the best materials for electric?
It's a high conductor of electricity, exactly. Same thing with platinum. Okay, same thing with platinum. Now, diamond is different. Diamond is not a conductor, right? Diamond has to do. Why do you put diamond on the tips of saws, like a table saw? Why are they diamond tipped?
Durability.
Durability. Diamond is the hardest material, so it doesn't cause the tips to wear down and fracture. Same idea here. Okay, material properties. Gold is not a high resistor. Okay, for example, take a look here. Iron, guys, focus. Iron, although strong, iron is very strong, more stronger than copper when it comes to material strength. Iron has a very high Young's modulus. So iron's strength is very high, but its resistance is very great also. So you wouldn't use iron in circuitry. You would use copper because it has a low resistance. Now, copper is extremely cheap and it has a low resistance. Gold has a lower resistance, but for gold, it's extremely expensive, okay? So the material property, again, the material property itself. Now, we're not going to make a generalization. You don't have to memorize, but you should know that copper is a traditional wire used because it has a low resistance. So material affects the resistance. There's no indirect or direct relationship here because there are so many materials. Okay?
Since iron is has lower resistance than copper, does that mean it's like denser or it has more particles that make up it, or like what makes it a greater resistance? then
I gotta look that up. I'm wondering. I'm guessing it has to do with the molecules and the interactions, but there's something else probably about it. Because gold is not a very porous material, yet it has very low resistance. So that wouldn't hold true with the density statement, right? So I don't know. Let me look that up. Maybe I'll get back to you.
That's what she joked with.
Mr. J would probably know that one actually, yeah. Because he knows the chemistry behind it. I'm wondering though, I don't know. Can somebody maybe look that up while we're waiting?
we don't have internet.
Ah.
We don't have internet.
Okay.
We can ask Siri.
So I'll try and look it up.
Siri uses internet.
Finally, temperature. Temperature.
You know what Siri's on my phone? My phone is
It's
You just think of that, did you?
it's very difficult.
I haven't done it yet.
Guys, stop. Somebody could have put up a Wi-Fi hotspot
I'm
earlier.
about to do that.
Yeah, I thought about that just now as he said that, right?
Yeah,
Do you have a hotspot?
I was getting the hotspot.
Wait, what do
Take
you
off
want?
The Wi-Fi. from the
Because my
school
Wi-Fi is
4G.
working perfectly. I don't know.
Why is it
Yeah.
You don't need Wi-Fi for Candy Crush, Gio.
So wait,
What's a Wi-Fi hotspot?
A Wi-Fi hotspot. The fourth thing, and it's not obvious on the diagram because you can't really see the color, but on the left-hand side, this is a low temperature. On the right-hand side, the temperature and the thermometer is all the way up. That's what they're trying to show here. So what can we make? What's the correlation? As the temperature increases, there's greater resistance. That's what we should write down there. Higher temperature, higher resistance. Again, having to do with computers. Remember we talked about overclocking and superconductors? Okay? If you can cool down a computer's components and elements enough, it runs much faster because there is lower resistance. Okay? All this stuff comes back to applications. So always think about applications of where you're going to see this.
Well, this is just along the latest related to
That's right.
Could we use chirp? Remember chirp?
I'm airdropping people.
I wonder if Chirp would work without internet. I'm sure it would.
The internet's on.
Oh, internet's on?
Yeah.
Back up.
I just sent out a mass airdrop.
No, you didn't, not to me.
You're not airdrop though.
Oh, okay.
Check your airdrop for the document if you want to pull it up real quick. Thank you. Awesome. Here's a random fact that I have written down in my notes that I remember from last year. Now, salt and water both affect the human body's resistance by lowering it a lot. And this is actually used to help lie detectors by sensing for sweat. So, you know when you go to, nobody's done this here, I assume obviously, but when people are brought into interrogations and they hook them up to a lie detector, what they do is, listen, what they do is they send a small current through your body. That current through your body is read by a machine. And those spikes in the machine when someone's lying, a lot of the time has to do with the electric conductivity of the body. And if they change the resistance, your body's natural resistance will change when you're sweating, when salt is produced. So when somebody's sweating because of that, it can produce a false negative. It could say like, somebody might just be nervous because they're being interrogated and they start to sweat. And that shows up as a change in the current in the person's body. So they'll see that spike. So that's why lie detector tests cannot be 100% proven true. Have you ever heard that before, lie detector tests? They're not always proven true. You need other evidence. It's just more evidence to help in the case.
You ever seen Ocean's 11? I think it was Ocean's 11.
I've seen all the oceans, go ahead.
Yeah, they, when the guy was being interrogated, because he's trying to like kind of mole inside the casino, he puts like a nail in his shoe, and then when it's so that his heart beats like, so he's always sweating throughout like the whole question. So it's just
So that when he's lying, it doesn't see the fluctuation.
Yeah.
That's kind of cool. Do you see what he's saying?
Yeah.
He's inducing pain on himself, so that he's sweating from all that pain. So he's always sweating. That's really cool. I like that application. I'll use that next year.
Yeah, I'll use it.
Let's take a nail.
Yeah, shut your mouth.
I'll talk about it
One
next year.
time, I was
use
in
it.
Russia and
Yeah, me question.
Guys, come on. Have respect. Classmates
my
talking.
aunt bought a lie detector test for her dad.
In Russia?
What?
This is in Russia?
Yeah.
Okay.
So like we were all playing with it, and then it was like my turn, and they put it on high for me because it electrocuted you if you're lying. And then they were like, "Do you love your brother?" And I started crying, and I took my hand out and didn't know what to say.
You don't love your brother?
I don't know if I did.
How old were you?
I was like,
He's another great sister.
7.
Oh, okay. That's kind of cool, yeah.
I'm sensing a future book deal in the next.
Let's take a look at an example now.
Or not.
Real easy. Real easy. So, I didn't talk about units yet. Let me talk about that real quick. Units of resistance are called ohms, hence Ohm's law. Okay? And we're going to see the symbol there. Okay? This is the symbol omega. as far as like Greek symbols are concerned, okay? This is the capital omega. Lowercase omega, remember, was frequency. That was that omega right there. Okay, that's not what we're looking at though. We're looking at capital omega. One's capital, one's lowercase. I know. They have the same general shape, the loops at the end. All right, so the resistance of an air conditioner is 21 ohms.
By that you mean you're going in, you're hooking out the air conditioner like walls and walls.
Yeah, the overall resistance. Yeah, there's a lot of internal components that have different resistances. The overall resistance of an air conditioner, I should say overall, it's good, James, is 21 ohms. What is the current in the air conditioner when it's connected across a potential difference of 115 volts? Okay? A lot of outlets in your house use 220 volts or 120 volts, just so you know. Those are the traditional voltages that come into a house. For something like an air conditioner, though, they'll use a 220 volt circuit. Okay, 220 volts. I just picked 115 to be random. So let's figure out what the current is in the air conditioner. So what's our law?
R equals R.
Yeah, either V equals IR or you could solve for R, either one. Okay, but this is the actual Ohm's law here. We're looking for the current, so let's solve for it.
So we want
I equals
V over R. V over
We
R.
went to
It's all right. V over R, V over R. Take the R and move it down. Okay, so it's simply 115 over 21. What are my units for current from yesterday? Who remembers?
Joule newtons per coulomb. Oh, amps.
Amps, there it is. Amps. What do I get for the answer?
You get 5.48.
I'll say 5.5 amps. Okay? So here's what this means. Ready? Let's make sense of this. A resistance of 115 volts of 21 ohms, wow, with a potential difference of 115 volts produces a current of 5.5 coulombs per second. Remember, amps are coulombs per second. So 5.5 coulombs of charge can pass a given area every second. Every second. James.
That's kind of weird.
Why is that weird?
Because 5.5 electrons bearing a coulomb.
Not 5.5 electrons, 5.5 coulombs of charge. That's millions of electrons.
Oh, okay. Oh, right.
Remember, an electron is 1.6 times 10 to the negative 19 coulombs, James, remember? So take the number 5.5 divided by 1.6 times 10 to the negative 19. That's how many electrons pass that area in a second.
Okay.
I want to explain what James is asking, please. This is really important that we understand the physics behind this, or the physical idea.
You get a lot of electrons.
Here's what we have, right? 5.5 coulombs of charge pass a given area every second. Well, there are millions and millions and billions of electrons in 5.5 coulombs. How do we figure that out? If I want to know the number of electrons, I take 5.5 coulombs divided by 1.6 times 10 to the negative 19 coulombs in every electron. That gives me the number of electrons. What is it?
3.4 times 10 to the 19.
This is how many electrons pass a given location every single second. So this is our example with the turtle race. There are this many turtles passing the given finish line at the exact same time. They're not moving fast, but every second, this is how many of them are moving across that finish line. There's a lot of electrons in that cross-sectional area because electrons are so small. Okay? Let's go to the last slide. Or we have two more slides, sorry. This is what I mentioned before about a variable resistor. It's called a pentiometer. Okay, it's called a pentiometer. And a pentiometer is a resistor that changes with the sliding contact area. So a light dimmer. Ever walk into the room and you can adjust the light using a dimmer?
I have that in my room.
That's what a pentiometer is.
I have that.
That's what a pentiometer is. The volume control. Take a look up here. This is a pentiometer. It changes the resistance and it increases the amount of decibels that you hear.
I like walking in my room. I have like that lighting, and I like to walk in the room and like dim the lights depending on who's over. You know.
Okay, anyway. I knew you were going somewhere with that. The third thing is your joystick. Anybody play video games? Okay. In certain video games, it matters how much you push on the joystick, right? If you push on the joystick quicker, the guy might start to run, or the guy will swivel quicker, or move slowly in certain games. And I'm picking like games like Call of Duty because I know y'all play those games. But he'll move slower versus moving quickly with the joystick. It's a potentiometer. That's all it is. It's a variable resistor. The signal changes. The signal that's processed changes based on how much you push or pull on that joystick. Okay. Finally, the last thing. Let's take a look at superconductors. This is what we talked about in class a few weeks back. This is the idea. Take a look at this. There's something called the critical temperature. Look at the resistance along the y-axis. Below 4.15, right? Look at the number here in kelvins. This is 4.15 kelvins. Below 4.15 kelvins, which is almost absolute zero, there is almost no resistance in the circuit. We say that the resistance here is negligible, and it is a superconductor. Okay, James?
There's also a very interesting temperature right above it. Resistance and nosedives. Right?
Yeah. There's a spike in the resistance. It almost becomes an infinite slope. It jumps up dramatically above that resistance. I don't know where the jump comes from now. I don't know. It's inherently in the graph, but I'm not sure where it comes from. And then there's a linear increase as temperature increases. That part makes sense, the linear increase afterwards.
It's just there. It's like nope.
The spike there, I don't know. That's two questions I need to investigate. That and what was the other one?
Come on,
Bring back the material and.
Why iron?
Oh, so Y iron is a higher resistor than copper, right?
Yes.
Okay, so I'll look up those two things and try and get back to you. Guys, a lot of the time, by the way, when you ask me questions, I don't ignore them. I actually look them up, and then I actually put them in the video that I record. So I include them in those videos. So I might not get back to you right away every time. But if I do actually come up with an answer, I'll end up putting it in the video. Because I usually record the videos after your classes. Because it helps me answer questions that are asked here in class. And I'm like, you know what, those are good things to add to the video. That's why I usually record the video afterward. Just so you know, your own knowledge. Okay? Section, take a look. Okay, 1 through 3, and then 2 and